moments expressed through t squared still equaled 1. This allows the momentum to remain unchanged.
Now, supposing for some reason your theory was concocted in such a way that even after all this renormalization takes place, even after all the worst-looking Feynman diagrams you can imagine, that if there was enough symmetry and at every stage that symmetry was correctly preserved in detail, the cancellation of the self-energies of the bosons might also be exact.
A one-loop diagram of virtual particle pair creation and annihilation can be viewed as a time slice through a three-dimensional time loop. What makes this a time loop is the cross-conjugate relationships between forward and reverse emissions and absorptions from the vacuum. In a way, we are looking at a diagonal cross-section of a conventional Feynman diagram of virtual particle pair production and annihilation, but with the emphasis on time direction and charge. If we apply three-dimensional time to time-reverse symmetry, examining particle pair production and annihilation, we get a unique interpretation of the relationship between charge and spin. Pair production consists of particle-antiparticle pairs. A forward-time particle could pair with a reverse-time antiparticle and/or vice versa. Charge could be defined as the product of the direction of spin and the direction in time. There could be four primary charges: positive charge forward, spin with direction of momentum; positive charge reversed, spin against direction of momentum; negative charge forward, spin with direction of momentum; and negative charge reversed, spin against direction of momentum. Examining the conjugate pairs and cross-conjugate pairs, we see equivalences. These four charges can be set around the complex unit circle, whereby positive forward and negative forward are complex conjugates on the positive real number side, and negative reverse and positive reverse are complex conjugates on the negative real number side. Though we can usually assume that positive forward and minus reverse, or minus forward and positive reverse, have a time-reverse symmetry, broken symmetries between positive forward and minus reverse, or minus forward and positive reverse, can be used to generate partial charges, where partial charge corresponds to variations in phase. In this case, though four possible spin directions can be derived, time-reverse symmetry between positive forward and minus reverse, or minus forward and positive reverse, reduce spin to only two directions: left-handed spin and right-handed spin. Using these relations, other spin quotients can be derived that are consistent with the Pauli matrices and Bloch sphere. What about fractional charge? How would fractional charge work? Assuming when a Fermi particle pops into existence, such as an electron-positron pair, it comes into existence with a slight time reversal asymmetry such that the electron and positron together act as a quasi-boson with a slight perturbation.
You plunk a quark down in empty space, and it starts to have an effect on the vacuum. In quantum mechanics, what we call empty space becomes the vacuum, and the vacuum is a very complex medium, not empty at all, contains virtual particles, and the essence of asymptotic freedom, which emerges from the calculation, is that if you plunk down a charge, its effect on the medium is to produce more charge. The charge builds up. That property of asymptotic freedom is a calculable property of the fundamental theory of QCD. It involves calculating the action of what we call empty space, the virtual particles, in reacting to charge and dressing charge. How the effective charge, the ability of particles to radiate, gets smaller and smaller as the amount of energy and momentum that is conveyed in the radiation gets larger and larger. One can start to trace out the energy momentum dependence of the effective charge, the probability of radiation, as a function of how violent the disturbance in the energy momentum flow that radiation makes.
Let this slight perturbation have a resultant charge, which can be polarized by either the electron or positron. However, the polarity and potential of this charge is uncertain, allowing slight offsets between positive and negative charges. From this, partial or fractional charges can be derived.
All of you know that electrons in a Fermi gas have a density of states which is independent of energy, but if you put on a magnetic field, that density of states breaks up into a set of discrete Landau levels. There was no energy gap in the system if you ignore electron-electron interactions. As soon as the interactions are turned on, a gap opens, and there are charged quasi-particles which have fractional charge. We know a fair bit about the charge of these quasi-particles. We don't know so much about the fractional statistics that they are supposed to exhibit. Many other states were found that were not so readily understood. You can see from this picture that there's a whole family of phenomena occurring that seem to emanate from the half-filling point. The half-filling point not itself showing a fractional quantum Hall effect. The concept of composite fermions was developed, the strongly correlated electron system in the lowest Landau level with the electrons all interacting with one another. The composite fermions are experiencing a magnetic field which is not just the external field, but as I say, it's corrected by all the flux quanta attached to all the other electrons. One can understand that picture of all those other fractional quantum Hall states in a very intuitive way. Instead of thinking of these as fractional states, you can now think of them as integer quantum Hall states, but not of electrons, instead of these things called composite fermions. And you might guess that this point here, this special point, which is the half-filling, is somehow a Fermi sea, a Fermi liquid of composite fermions. Well, this is quite remarkable, because after all, you're in a lowest Landau level, which without interactions is absolutely free of any dispersion. And then all of a sudden, by turning on these interactions at half-filling, it reconstructs itself in some way into something like a Fermi liquid.
The other famous feature of confinement that was thought to be very paradoxical in the early days was the fact that quarks have fractional charge. Here we have a modified U1 because the symmetry of the state with the condensate is not the original color symmetry or the original electromagnetism, the one that survives and gives a massless vector boson is a combination of the two. Just as in the standard model, the emergent photon is a combination of what was originally the hypercharged boson and one of the weak isospin bosons. The original photon was described by this charge matrix. If we consider a gluon, which in color space acts with the same matrix, then acting with these two on the Kronecker delta function, the massless vector boson, which we can get by taking a combination of those two, is easily identified as this one. In fact, even though confinement has been implemented by this simple symmetry rating superconductivity mechanism, we find that fractional charge is gone. If we measure fractional charge as we should, according to what the photon thinks is the charge, then we find that all the particles have integral charge.
Time reversal asymmetry can also be applied to baryogenesis, accounting for the initial asymmetry between baryons and antibaryons, matter and antimatter.
We think at the beginning of the universe, in the Big Bang, we had equal amounts of matter and antimatter being created. And yet, if we look at the universe around us today, we don't have equal amounts of matter and antimatter, we just have matter. And we know this because if matter and antimatter meet, they annihilate, they explode and release loads and loads of energy, and this quite clearly doesn't happen around us. Now, in order to go from a universe which consists of half antimatter and half matter to a universe that consists all of matter, then something really big and fundamental must have happened. And one condition for this to have happened is for an effect called CP violation to come into play. Now, CP violation is nothing more than a difference in the behavior of matter and antimatter. And quite clearly, if we have half matter and antimatter to start with, and we now have matter today, they must behave differently in order to reach that state. We don't really understand this effect, but we want to understand it in particle physics. It's a very important unanswered question in physics and particle physics and astrophysics all over the place.
If we use the standard figures, where for every matter particle there's roughly 1 billion photons, this suggests that the ratio between matter and antimatter is slanted towards matter by about, 1 part per billion. Though slight, the basic existence equations can account for this difference. If we let A represent matter and B represent antimatter, the ratio is small, but A asterisk minus A is slightly larger than B minus B asterisk. Where A and B correspond with some present moment, A asterisk minus A is slightly into the future and B minus B asterisk is slightly into the past. It can be argued that the asymmetry between baryons and antibaryons is superficial. Forward time baryons are symmetrical with reverse time antibaryons, with the exception that forward time baryons are slightly into the future relative to reverse time antibaryons, which are slightly into the past relative to the forward time baryons. If we allow quantum spin to be a property of three-dimensional time, then the asymmetry can be reduced to an issue of chirality and helicity. For instance, in weak interactions, fermions appear to have a preference for spin away from the direction of motion. This would allow us to cross-conjugate forward-time baryons with left-handed spin and reverse-time antibaryons with right-handed spin. But then, there was the Wu experiment, and then two unusual decays were uncovered for charged, strange mesons. In 1956, physicist Chien-Shiung Wu conducted an experiment on behalf of physicists Tsung-Dao Li and Chen-Ning Yang to wrest the relationship of parity symmetry with physical law. Radioactive cobalt-60 was cooled by liquid helium to temperatures near absolute zero and aligned with a uniform magnetic field. The thermal vibrations of cobalt-60 were reduced enough to study its beta decay process, nearly one emission at a time. Wu found that when the cobalt-60 nuclei spins were polarized with the uniform magnetic field, significantly more electrons radiated in the opposite direction with opposite spin. In other words, there were significantly more electrons with left-handed spin than electrons with right-handed spin.
The thing that's interesting is that if you measure the spin, electrons are spinning as they come out. If you measure the spin, you find out that they're spinning to the left. That is a definite significance that the electron, when it comes out of the disintegration, is turning this way. So all we're saying is that the right and left symmetry law is not valid. But I have to mention that conservation of parity, because you may have read in the papers that the law of conservation of parity has been proved wrong. It should have been written, but it's much easier to understand. The principle that you can't distinguish right and left has been proved wrong.
The Wu experiment shows us that the forward-time Fermi particles are able to condensate, whereas the reverse-time anti-Fermi particles are radiated away. Though this has the appearance that weak interactions have a preference for reverse-time anti-Fermi particles, the forward-time Fermi particles are able to condense first. For a slight moment, together as cross-conjugates, the forward-time Fermi particles and the reverse-time anti-Fermi particles can act like quasi-bosons. These quasi-bosons can intermediate quasi-weak interactions. The reverse-time anti-Fermi particles radiate away, appearing as electrons with left-handed spin, and the forward-time Fermi particles do not radiate away and are bound. Right-handed fermions would appear less prevalent, being bound in matter, and left-handed fermions would appear more prevalent in the form of radiation. This suggests that matter and antimatter are viewed incorrectly. We can treat the negative energy aspect of the Dirac equations as a negative time loop, treating it as a negative three-dimensional time scalar. If we plot the maximal and minimal values for t prime and t squared into three-dimensional coordinates, using t sub 1, t sub 2, t sub 3, where t prime is t sub 3 and t squared is t sub 1 times t sub 2, we quickly see that the time wave can be expressed three-dimensionally, in part using the Pauli matrices. When the time loop is expressed in the language of quantum mechanics, it satisfies the antimatter components of the Dirac equation.
There's only 3 Pauli matrices, sigma X, sigma Y, and sigma Z, and we need 4 matrices that have those relationships. Here's the trick. The Pauli sigma Z trick is 1 and minus 1, so here we're going to have I and minus I. That gives us the extra degree of freedom. So we have 4 Dirac matrices instead of 3 Paulis. So that says the eigenvalue for the energy for this one's mc squared, minus mc squared, minus mc squared. So you can see that the particle solution split into 2 kind of particles, 1 particle with positive energy, 1 particle with negative energy. Now, the negative energy is troublesome. We have 2 kinds of solutions in terms of the energy eigenvalues. Here is 1 pair of solutions, and here's the other pair.
The antimatter aspect of the Dirac equations may have been misinterpreted. The convention is to assume that matter is composed of particles distinctly different from antimatter, which is supposed to be composed of antiparticles. The hidden assumption of 1 time dimension locks in this interpretation of the Dirac equations. If we assume that matter consists of both particles and antiparticles cycling in and out of phase on opposite sides of a time loop, such as with an electron orbital around a hydrogen nucleus, the issue of missing antimatter disappears, and a complex relationship between time, energy, and mass appears. We could argue that matter is composed of both particles and antiparticles, but moving in opposite directions of time. Matter would be the right or stable configuration of particles to antiparticles, whereas radiation would be the wrong or unstable configuration of particles to antiparticles. Applying this to the excess baryon asymmetry equation, we could associate the excess baryons with the right configurations and the cosmic microwave background photons with the wrong configurations. This can be extended to the CKM matrix and the measurement of sine 2 beta time-dependent parameter of CP violation in B meson decays.
For 3 families, the mismatch between the up quarks and down quarks means that the weak charge currents involve these 3x3 unitary matrices. The hadronic part is the CKM matrix. The relevant elements comes from beta decay and kaon decays and heavy bottom quark decays and charm decays, and eta represents the CP violation. There's 2 aspects to unitarity. The first aspect is the diagonal elements must be 1. The other aspect is that V dagger V 3, 1 should be 0. This is known as the unitarity triangle. Now, why is it a triangle? Well, these are complex numbers, and any complex number can be represented as a vector in a 2-dimensional vector space. This is a vector, and that's a vector, and the last one's a vector, and so they should add up to 0. They should form a triangle. Turns out if there were no CP violation, then all of these would be along the real axis, and so somehow the area of the triangle is measuring the amount of CP violation. One expects to have in the rho eta plane, by dividing that out, one of the elements just is at 0, 1. That's this vertex. These angles in this parametrization are called alpha, gamma, and beta. Vector is rho plus I eta, and this is 1 minus rho minus I eta.
This framework allows a re-examination of the rho eta plane used for plotting the unitary triangle, but in terms of temporal coordinates. T1 would equal a length of A slightly shifted forward into the future, and T1 prime would be the length of B slightly shifted backwards in time. Remember, we had designated this as period. With this dimension of time corresponds here to both A and B having a change in their passage of time. If we examine the mathematics for measuring decay rate, The decay rate can be associated with the periods of time component, and the mean lifetime can be associated with the passage of time component. Since the base expression for mass equals the absolute value of t prime times t squared, there are two possible observations. First, we are dealing with decay rates of time, so we can set the passage of time as the vertical component for both b minus b asterisk and a asterisk minus a. This forces the period of time coordinate to be different between b minus b asterisk and a asterisk minus a, resulting in a time reversal asymmetry. The longer the lifetime of a particle, the less uncertainty there is in the mass energy. The shorter the lifetime of a particle, the more uncertainty there is in the mass energy. On the other hand, we are using a model compatible with massless particles, so we can set the present time as the vertical component for both b minus b asterisk and a asterisk minus a instead. In this case, the period of time coordinate is different between b minus b asterisk and a asterisk minus a, resulting in a different type of time reversal asymmetry. In the first case, there is a mass invariance, whereas in the second case, there isn't. In the second case, b minus b asterisk and a asterisk minus a can both have the same passage of time, that is, the same mass, though there is a break in simultaneity. Re-examining CPT symmetry, time reversal asymmetry is equivalent to a charge parity asymmetry. If we take both types of time reversal asymmetry, where the passage of time coordinate values are inversely proportional to their corresponding linear time values, then the uncertainties between b minus b asterisk and a asterisk minus a smooth out, and a relative to b equals b relative to a, even though a relative to a does not equal b relative to b. This isn't a contradiction. This is an identity crisis, where the Pauli exclusion principle and the inclusion principle correspond with quantum entanglement. If a equals b, then a over b equals 1, and the identity constant is 1, meaning there is only one particle, physical state, field, etc., depending on the application. If a is greater than b, then a over b is greater than 1, and there are at least two particles, states, fields, etc. When a over b is 1, this corresponds with the inclusion principle. When a over b is greater than 1, this corresponds with the exclusion principle. In quantum mechanics, it is impossible to know both a particle's momentum and position simultaneously within an accuracy greater than h bar. This is known as Heisenberg's uncertainty principle. Using three-dimensional time, we can apply both the inclusion principle and the exclusion principle simultaneously and account for the uncertainty principle, allowing for the basic existence equation to apply generally to quantum mechanics. We can argue that charge parity asymmetry and time reversal asymmetry are indicators that CPT symmetry is incomplete as a fundamental symmetry of physical law. The basic existence equations can account for mass invariance using 3 dimensions of time. So how do we account for an invariance or break in this symmetry? M violation. What is M violation? Since charge parity and time reverse symmetry are equivalent, charge parity and time reverse symmetry together in this 3-dimensional time model is equivalent to mass symmetry. M violation becomes central to the quantization of gravity. Using the classical gravitation equation, Kepler's second law, and substituting a temporal radius for r, we get the following. If we assume Einstein's equivalence principle, a variance in acceleration or mass would indicate an inequality, and t squared could not equal 1. However, if the two masses are significantly different, then t squared can have different values relative to different rates of the passage of time in correspondence with each mass without violating Einstein's equivalence principle. If two particles are in the same state at the same time, and it is not possible for them to change state in order to avoid violating the exclusion principle, the identity of each separate particle can become indistinguishable, resulting in just one particle. One of the masses is converted to a relative time and conserved through a change in the rate of the passage of time. The gradient of change in the rate of the passage of time of the massive object is the gravitational field of that object. Since we are dealing with various rates of the passage of time, differing mass distributions of point particle masses, the difference in the passage of time between various masses in different locations will displace the center of mass towards equilibrium through uniform invariant motion, inversely proportional to the distance and proportional to the period of time the motion takes place in. We know this simply as gravity. These four potential relations have a complex conjugate type of relationship where, relative to the lighter mass object, we get the following frames of reference, and relative to the heavier mass object, we get these frames of reference. From here, we can derive two equations for acceleration, one relative to the falling object, the other relative to the massive body. What we can see is that these two equations are conjugates. Therefore, both masses are experiencing the same acceleration, though not in the same way. Looking at the passage of time component in the temporal definition for mass, the relationship between temperature, mass, and so on are byproducts of viewing the universe through an inertial frame of reference. Referring back to the sine 2b measurement, this double angle gives us a value of approximately 0.69. This is almost the value for the sine of 45 degrees, suggesting that the time-dependent parameter of CP violation in B meson, as predicted by the CKM model, may correspond with a phase transition. In our model, this phase transition could be between cross-conjugate pairs or between forward time particles and reverse time antiparticles. The transformations between left-handed to right-handed or right-handed to left-handed fermions, which is associated with generating a mass associated with weak interactions and the neutrino seesaw mechanism, is better understood through cross-conjugation and cross-symmetry. We can speculate that the values associated with dark energy correspond with phase transitions of quantum fluctuations over periods of time that correspond with the history of the universe. This suggests that there may be a relationship between the time-dependent parameter of CP violation in B meson decays predicted by the CKM matrix and the values associated with the lambda CDM model of the universe. These may correspond with the same phase transition, but reflected on severely distinct timescales. According to quantum vacuum zero-point energy, the lowest possible energy a quantum mechanical system can have is the ground state, which too undergoes quantum fluctuations. Symmetries between beta decay-like and reversed anti-beta decay-like phenomena could oscillate in a time loop as a temporal superposition of a hydrogen atom-like structure. These diagonal symmetries appeared to take into account charge parity violation. A forward and reverse time loop model resembles aspects of Heisenberg's uncertainty principle, incorporating a new principle into quantum entanglement, the inclusion principle. The inclusion principle and the Pauli exclusion principle work together to account for quantum entanglement, but in a new way. The basic existence equations and three-dimensional time can be applied to quantum entanglement, creating a dichotomy between the Pauli exclusion principle and a new concept, the inclusion principle.
It's a little technical, but very paradoxical, is that we had a rule back for atoms that no two electrons can occupy the same state. It's called the exclusion principle. And we thought we understood that that was necessary according to quantum mechanics and relativity. It has to be. And with the quarks, we find the exact opposite rule. Two particles tend to occupy the same state. The exact opposite. Seems to be contradictory with principle.
we don't find experimentally any such particles. Now, everybody's looking for them. But it looks as if they exist at all, they have to be extremely heavy. Then the problem is, very good, if they're extremely heavy, how, compared to a proton, say, how is it when you put three of them together, you get a light object that's not heavy, like the proton? There are technical ways of arranging it, but they're always complicated. The situation is, as it always is when we're near the answer, it looks much simpler than it has any right to be. And the question is, what way do we have to think about it so that we understand its simplicity? That's where we stand now.
Starting from a quark soup of quantum fluctuations, there is some probability for structures to form with varying degrees of stability. For instance, some quark configurations, such as mesons, are not very stable, whereas other configurations, like neutrons or protons, are more stable. Using cross-symmetry and cross-conjugation, we can create a neutron from quark fluctuations. From this, we can transform a neutron into a more stable proton. Because protons carry charge, a virtual electron-positron pair has a probability to polarize with the proton. The reversible process of electron capture, or inverse beta decay, could spontaneously form an oscillating temporal loop of beta decay, anti-beta decay, beta decay, and so on, which can account for both quantum electrodynamics and quantum chromodynamics. What this suggests is that matter is composed of both particles and antiparticles. We have already examined how 3 dimensions of time and the basic existence equations can account for how this could be possible. The equation used in baryogenesis to account for the asymmetry between matter and antimatter can be reinterpreted. The numerator corresponds with an excess of baryons over antibaryons, and the denominator corresponds with the CMB radiation left over from baryon-antibaryon annihilation. Therefore, there is no missing antimatter or excess of baryons. Rather, baryon and antibaryon structures have stable and unstable configurations such that an emergent universe can arise from quantum fluctuations without a Big Bang. The asymmetry between particles and antiparticles is both a driving mechanism and cause for the stability of matter. This model can be used to account for physical phenomena associated with nickel-titanium at negative Kelvin temperature.
This giant complex of buildings overlooking San Francisco Bay is the Lawrence Laboratory at Berkeley. Some of the world's most advanced research in theoretical and practical physics is being done here. For some years now, a small group of scientists attached to the laboratories have been investigating this, a curious metal called nitinol. It has certain anomalous properties not yet fully understood or explained. It's caused considerable interest. It has generated some controversy. It may have profound consequences. Nitinol had apparently unique properties. The head of the laboratories was Nobel Prize-winning physicist Professor Edwin McMillan.
Well, this is a piece of nitinol which was made in the shape of a coil spring. And the property of nitinol is that when it's